Right, we're going to touch on a concept that we've previously touched on, keto enol tautomerization. So, for example, when you have a ketone, it's generally going to be in equilibrium with its enol form. So then this is the ketone, right? And then this is the enol. Enol, en like alkene, all like alcohol, enol. Note that these compounds are different from one another, right? And basically this hydrogen goes from being down there to being attached to this oxygen. In general, the ketone form is much more favored over the enol form. For example, in equilibrium, this enol forms up, let's see, get the right number of zeros, 6 zeros, 0.6 zeros, and then 1%, right? So it's a very small amount. However, we can make it more predominant based on the compounds and the bases that we can eventually use. And even though this doesn't make up a lot of the component in equilibrium, it's still there and so can still react, right? Note that these are not resonance structures of one another. In resonance structures, we only move pi bonds. Here we move the sigma bond, right? That carbon hydrogen and that oxygen hydrogen bonds. So these are not resonance structures. And then again, the ketone is generally favored. And this transition can be acid or base catalyzed. In terms of the mechanism, check out the work along, but it's something that we've done before. Note that it's practically impossible to prevent this. You're always going to have some acid or some base in any kind of reaction. It's almost impossible to get rid of all the acidic or basic protons. There's always going to be at least a little bit there. And so this equilibrium will always be there.